Okay, good morning, everybody. So the previous lecture did not record correctly, so I'm not 100% sure of where we left off. I'm pretty sure we talked about preconditions, though. Just in case we didn't, I'm going to review the first this part of the lectures. If we did cover it, then I apologize, but I really don't know where we left off. Okay, so a method precondition is something, is a condition that must be true before a caller uses a method. And so for example, some methods require that one or more conditions be true before the method is run. So if you wanted to, for example, divide a point, divide the coordinates of a point by some scalar value s, it's pretty important, it might be important that s not be equal to 0. Let me just skip ahead to the slide for a second. All right, so here's this method called divide. It's inside the point2 class. So inside point2, if we look at the divide method, if you look at the what it actually does, right? So it takes in some double value s and divides the x and y coordinate of the point by s. Right, now obviously if s is 0, there's something, if s is 0, then mathematically you're doing something unusual. Right? So if x or y, if they're not 0 and s is 0, then the result is positive or negative infinity in Java. Right? If x or y are equal to 0, then the result is not a number in Java. The positive and negative infinity may not be so bad, but the not a number causes all sorts of problems later on. And so whoever's writing this method might decide that s really shouldn't be 0 if you want to use this method correctly. Okay, so let me back up. Right, so a method precondition is a condition that the caller of the method must ensure is true immediately before calling the method. Now notice that where the responsibility lies here, right? It's whoever is using the method. So whoever created the method is not responsible for ensuring that the precondition is true. Right? If someone wants to use the method, then they have to make sure that they call the method with valid inputs. Right? So if your method has a precondition, then you should document the fact that the precondition exists. Right? Ideally, you would put it in the javadoc comment for the method. Right? And now javadoc doesn't actually have a dedicated tag for this. So it's got tags for documenting the parameters and things like that. Right? But it doesn't have a tag for documenting preconditions. And so what ends up happening is you end up documenting the preconditions using some sort of, in the description somehow. Right? So for example, in divide, if you look at the documentation for the parameter, right, there's an indication that s must not be equal to 0. Right? So there's the documentation for our precondition here. Now, the responsibility for meeting the precondition is with the caller, right? So it's not with the implementer. Right? So if you're the one creating the point2 class, then you can decide what happens if the precondition is not satisfied. Right? And so what that means is that you can do anything you want when a precondition is not satisfied. Right? So for example, here we just ignore the fact that s might be 0, and you go ahead and implement your method. Right? So you don't even, we've taken the approach that we've warned people, don't use 0. If you do, it's your problem. Right? Now, there is an issue with assuming that preconditions are true. Right? So as the implementer of the method, if you take this approach, there are all sorts of consequences. Right? Mostly these consequences affect the caller or the user of your class. Right? So what might happen? Well, your method might end up returning the wrong value. Right? So that particular method doesn't return a value. Instead, what might happen is, right, the method might put the object into an invalid state. Right? So in this particular method, if s is 0, right, you end up with a point whose coordinates are either infinity or not a number. Right? And you might argue that either one of those cases, that point is no longer a valid point. Right? Or it's no longer a useful point anyway. Other things that can happen, so the method might encounter some kind of error, right? And if it does, it might throw an exception, right? And that exception probably won't be documented because you're not expecting to throw that exception, right? So that's not good either. And then the method may not be able to do everything that it says it wants to do or should do. And so that's an example of not satisfying its postconditions, which we'll talk about in just a second. So again, here's the example of what happens when you use that version of dividing by 0, right? You end up with infinity and infinity. All right, so the approach taken by the Java standard library is to actually explicitly check that the preconditions are satisfied. Right, so even though it's not the responsibility of the implementer to ensure the preconditions are true, right, you can assume some of that responsibility and at least test, are the preconditions satisfied? Right, and if they're not, you can throw an exception to tell the caller or to indicate to the caller that they've done something incorrect. Right, and so you've seen exceptions in the first 2 assignments already. Right? You should have also seen them in Python, so in 121. Exceptions, they are available in many modern programming languages. Some of the older programming languages don't have them, so notably C does not have exceptions. And so you have to do something else. Exceptions in languages like Java and Python, they're that term is shorthand for exceptional event. Right? So in other words, when something unusual happens, you might throw an exception. In Python, you would raise an error. Right? It's the same thing. And so the way it works in Java is if a method decides to throw an exception, the method stops running where the exception is thrown. It makes an exception object and hands that object back to whoever called the method. If whoever called the method has some code that deals with the exception, then everything stops there. If the caller doesn't have code to handle the exception, whoever called the caller now gets the exception. Right? And so on and so on and so on until you get back to the main method. If the main method doesn't handle the exception, then the program stops. Right? So creating an exception object and handing it to the runtime system, that's called throwing an exception in Java. Right? Python, you'd raise an error. There's lots of different kinds of exceptions that you can throw. We've been using illegal argument exception. So illegal argument exception is the exception that you normally throw when you're testing the inputs to a method, and you discover that one or more of them are invalid. If you're using a list or any indexed collection, right? So something like a string, a list, just a collection, or an array. If you use an invalid index, you'll get an index out of bounds exception. If you try to use an object, so if you try to use a reference that is null to call a method, you'll end up with a null pointer exception. Right? So remember, null means no object. If you're trying to call a non-static method, you need an object. Right? So if you use null to call a non-static method, you end up with a null pointer exception. All right, so from the assignments, you know that to create and throw an exception, you make an exception object, right? So new illegal argument exception, and then you throw that object, right? So use the keyword throws. Right? Your code stops running immediately after the throw statement, right? And that means that any code after the throws statement never runs, which is good, right? You want to stop, so in a method that has a precondition, right? You don't want to change the state of the object if you have an invalid input. Right? You want to test for the precondition first. If the inputs are invalid, you want to stop before you do anything else. Right? So you want to test and throw before you do anything else, like this. Right? So instead of deciding to do anything in this particular method, if the value of s is 0, we're going to choose to test for that condition. Right? And if that condition is true, we're going to throw an illegal argument exception. Right? So if the input is invalid, throw an exception. Now the rest of this stuff never happens. Right? So we never change the x coordinate of the point, we never change the y coordinate of the point, and that's good. Right? The caller is left with a point that is still in its original state. Right? It hasn't been changed by an illegal input value. Right? So make sure you test for your preconditions first and throw the exception. Right? Don't do this and then test for the precondition afterwards, right? If you just divide by s right, if you just divide by s right away, you end up putting the point into an improper state. Right. So preconditions are pretty straightforward, right? So they're just the conditions on the inputs of the method. A postcondition is what the method promises will be true after it finishes running, right? Immediately after it finishes running. Again, these are conditions, so technically they are statements that are true or false. Now, unlike the precondition, the responsibility for meeting the postconditions lies with the method, right? So whoever creates the method, they are the ones who are responsible for ensuring that the postconditions are true. Right? If your postconditions aren't true, then there's something wrong with the way you've implemented your method or constructor. Right? All right, so remember, postconditions, they are conditions, so they are something that are true, or they are statements that are true or false. Now that's really awkward to, so essentially the postconditions and preconditions are mathematical statements about what your method will do, right? So that means it's very awkward to write these things. So normally people don't write postconditions as true or false statements, right? So instead they describe what is it exactly the method will do, right? So for a non-static method, right, your postconditions might involve the value that's returned by the method, right? So your method might say always returns the value 2, right? So that's your postcondition. Some methods change the state of your object, right? So mutator methods will change the state of an object. The postconditions for those methods will involve the fields of the methods, right? So the data that the object is holding. And then some methods take in an object as input and then modify that object, right? So they call some methods belonging to that object, changes the state of that object. So some postconditions will involve the arguments that are passed to the method, right? Essentially, the postconditions describe what the method will do given valid inputs. Okay, so again, postconditions are normally described in the documentation of the method using plain English rather than mathematical expressions. Right? So what is the postcondition for the method x? So this is in the point 2 class. Right? So what does x do? Well, it returns the x coordinate of the point. Right? So that would be your postcondition here. Right? If you have a return statement, if you have a return tag, right, that's also part of the postcondition. Right? This method promises to return the x coordinate of the point. So that looks pretty straightforward. All right, so it's possible, but it's usually very awkward to express a postcondition as an actual condition in Java. Right? And so if you look at this thing here and you say, well, how would I mathematically describe this postcondition? It's not at all clear what you would do here. Right, so let me go into Eclipse for a second. So there's our method x, right? I'm going to rewrite it a little bit. So instead of returning this .x immediately, I'm going to introduce a variable called result, right? And then I'm going to return result. That lets me attempt to write a postcondition. Okay, so a potential postcondition, or the quote-unquote obvious postcondition for this method might be, well, the result is equal to this .x, right? But notice there's 3 question marks here, right? So if you stop and think about exactly what you're writing here, at first glance, when you look at this, you might say, well, yeah, that looks right? That should be the correct postcondition, right? And that's true, assuming you can actually see the code that's in the method, right? So if I can see all of this, then that looks like a sensible postcondition. The problem is if you can't see the source code, that postcondition is not sufficient, right? Why isn't it sufficient? Because someone can do something silly like this, right? Obviously, this is incorrect, right? You shouldn't implement the method this way, right? But if someone was to implement the method this way, or to put in some sort of code that changed x, right? Then this postcondition is no longer correct, right? that postcondition says the return value should be the current value of x, but the real postcondition is the return value ought to be the original value of x, right? So really what you want is some way to remember what was the original value of x. Oh, sorry, double. And now your postcondition is looks like that, right? Okay, so the result should be equal to the original value of x, right? And now if you test this postcondition, right, you would realize for this particular implementation of the method, right, you would realize that in fact something is wrong with your method, right? If you have a point whose coordinates are, say, 5 and 2, right, the original value of x is 5, then x gets changed to 0, right? The result gets set to 0, and the result is the value of 0 is returned, right? And your postcondition is now false, right? So that indicates that there's actually something wrong with your method. Right? So that lets you catch that particular error there. Right? So there's also nothing from stopping somebody from writing that, right? And so your actual postcondition that's there is correct, but it's incomplete, right? This method promises to return the original x value of the point, or the value of the x coordinate of the point when it was when the method was called, right? It's not supposed to be changing the state of the point, right? And so your complete postcondition is in fact something like that, right? So the y coordinate of the point remains unchanged, right? And the x coordinate that's returned is equal to the original value, the value that's returned is equal to the original value of x. I said that's complete. It's actually not complete, right? So it's not complete yet. Right? So now that postcondition is true, but the code is still incorrect, right? The original value of x, the x coordinate of the point has also changed, right? So is dot x. So the complete postcondition is in fact that, right? The value that's returned is the original value of the point, and the state of the point remains unchanged. So again, so this is not at all obvious, right? So no one in their, well, almost no programmer would come up with this the first time they've heard about postconditions, right? And so that's why I said in the slide, where'd it go? Possible, but usually awkward to express a postcondition as an actual condition in Java, right? These are surprisingly tricky to get correct. And so there's a different version. I called it old x and old y here instead of orig x and orig y. Right. You might wonder why final is being used here. So final in Java means that you can only assign a value to old x once. So here we assign a value to old x, so that's the only time we can do it. Right? And that simply prevents somebody from changing old x inside this method later on. Right. Similarly with old y and result. Okay, so for a mutator method, the idea is similar, right? So for a mutator method, the postconditions also involve the fields of the object. Right? Actually, this one involves the fields of the object as well, right? But in a mutator method, the mutator method is going to change the state of the object, so this one's definitely going to involve the fields, right? So new x, x that takes in a double value changes the x coordinate of the point to new x. Right? So if you were to try to formulate this postcondition, the postcondition for this method, it would be something like the following. Right? So you want to ensure that the x coordinate of the point has been set to param x. So param x is the value of the parameter when the method was called. Right? You want to make sure that the y coordinate of the point hasn't changed. Right? So this y equals old y. Right? And you want to make sure that the returned value happens to be equal to the object. In this case, you want to make sure that the return value is equal to the object that was used to call the method. Okay, so up here, so I don't care about the original state of x in this case, right? Because I'm going to change the state of x. Sorry, I don't care about the original x coordinate of the point because I'm going to change it anyway, right? But I do care about the original value of the parameter, right? Because again, there's nothing from stopping somebody from changing the parameter, right? So inside the method, you might accidentally set new x to some other value, and then write this x equals new x, right? And so this method doesn't change the coordinate of the x coordinate of the point to new x, it changes it to 1, right? Oh wait, so yeah, that can't be, but no, that's fine. Right, and so that's why you need to remember what the original state of new x was, right? That's why I need param x up here. Okay, so you can technically write the postcondition for any method or constructor. It's hard to do, right? It's very awkward. So let's assume that you actually managed to write the postcondition for all your methods or for your method, right? Is there anything that you can do to actually test if the postcondition is true before you return from the method, right? And so the answer is, well, sort of. Right? So remember, the postcondition is a condition that's true immediately after the method returns. Right? So that means you want to check the postcondition after the return statement, but you can't. Right? You can't put any code after the return statement. So the best thing that you can do is stick in an if statement immediately before the return statement. Right? So you could, if you really wanted to, right, check your postconditions for all your methods before you return from the method. Right? Now, of course, this imposes a cost, right? So everybody who calls your method, they're going to have to pay the price of this postcondition being checked. Right? So here's the method set that changes the coordinates of the point to new x and new y. Right? You can formulate the postcondition as that condition there. Right? So set changes the x coordinate of the point to the original value of new x. Right? It changes the y coordinate of the point to, sorry, that should be, what did I do here? Old y equals this y. No, that's not right, sorry. I guess I never completed editing this slide, sorry. So that's param y. That. Let me get rid of this. So x equals new x. Oh, this is all wrong, sorry. Equals new y. Param y. Okay. Okay, so this version, so set changes both the x and y coordinates of the point. So we're going to remember what are the original values of new x and new y, right? When the method returns, or immediately before the method returns, we're going to check, is the x coordinate of the point actually equal to the original value of new x, right? Is the y coordinate of the point actually equal to the original value of new y, right? And is the result actually equal to this object, right? If that's false, we know that the postcondition is incorrect, right? And we can throw an exception or something else because we've screwed up in our method somehow, right? So for example, if that line there was uncommented, our method would be incorrect, right? And putting in this postcondition would let us immediately find out that there's something wrong inside of the method. All right, so instead of always testing the postcondition, right, you can do something else. So you can use what's called an assert statement. This is not super common in Java. It's more common in a language like C. And even there, it's not that common. Right? So you can use these things called assert statements. Assert statements, basically you pass it a condition that you think should be true. If the condition is false, then the assert statement will cause the program to stop. Right? So if the condition is not true, then you get an error thrown. Right? The nice thing about assertions is that you can turn them on and off, right? By using a compiler switch. So the idea here is that while you're developing and debugging your program, you leave assertions turned on. Right? When you're confident that your code is correct, you turn the assertions off, right? And now the assertions don't occur anymore in the code, right? Or they're not checked at runtime, right? And so that that gives you the advantages of testing your postconditions, right? For debugging and developing. But your users of your code don't have to pay the price of testing the postconditions all the time. Yes?
It's an alternative to the if statement, right?
Yeah, it looks like that.
Okay.
Yeah, it looks something like that instead, right? So you assert that this condition is true. If that condition is false, you get an error at that line. Oh, this is all messed up too. Sorry, this yeah, there was a copy and paste error. So this code here should be the code from the previous slide. Okay, so by default, assertions are turned off in Eclipse. Right? If you want to, you can turn them on. That's how you turn them on. I'm not actually going to ask you to use them in this course for anything. If you want to see how they work, though, you can play around with them in Eclipse and see how they work following these instructions here. All right, so you might wonder why I'm telling you about all this, right? So what's the take-home message from all this, right? So you need to remember what a precondition is, right? So precondition, some condition that must be true before the method is called, right? The caller of the method is responsible for your preconditions, right? Your postconditions simply describe what the method is expected to do, right? Given valid inputs, right? Technically, the postconditions are conditions, so they're statements that are true or false, right? So they're essentially mathematical, they're logical statements, right? But they're very awkward to write, right? Again, because they're mathematical statements, right? In principle, so in practice, you should test for preconditions, right? Throw an exception if the precondition is not satisfied. In practice, for most code that's written, the postconditions are never checked explicitly, right? So in other words, no one does this, right? At least in most code that's written, right? Now, you might ask, so, I mean, why am I telling you about all this, right? So the answer is because there is a lot of code that's written where the correctness of the code is very important, right? So anything that is safety critical, or any code that's controlling something that's where if there's a failure in the code, bad things will happen, right? In those particular applications, right? It's really important, right, that your code be correct. And so those applications, it's not uncommon that you're going to want to formally describe your software, right? That is, you want to write down explicitly what are your preconditions, right? Explicitly write down what are your postconditions, right? And you would really like your software to check your preconditions and postconditions for you, right? So there are languages that are meant for safety critical applications where all of this stuff happens for you. Right? You tell the software or you tell the programming language what your pre and post conditions are, right? And it does all the magic of this stuff here and this stuff here for you, right? So it inserts all of the necessary code that you need to test your preconditions and post conditions, right? So the language is actually, there are languages that actually support this sort of thing. Java is not one of those languages, right? But these languages do exist. There's a fourth-year course called Formal Methods. That talks about this sort of stuff in greater detail, right? So if you end up taking that course, you'll end up revisiting preconditions and postconditions all over again. You might even see some of these languages that actually do or perform precondition and postcondition testing for you. Okay, so there's one more thing we need to talk about that involves conditions, and these things are called your class invariants. So an invariant is another kind of condition, right? Now, condition can be true or false, right? So it's just a logical statement. An invariant is a condition that's always true, right? And so that's why it's called an invariant, right? So it's something that, it's a condition that never changes and is always true. Right? So a class invariant is a condition regarding the state of an object that is always true, right? Now, if your class has an invariant or multiple invariants, right, then your class is responsible for ensuring that those invariants are always true. Right? So that means when someone calls a constructor, the object that is created, its class invariants are true. Right? If somebody calls a method on your object, when the method is finished running, the invariants are again true. Right? While the object is being created or while the method is running, the invariants can temporarily be false. Right? But when everything is done, the invariants become true. Many classes have no interesting invariants. So for example, point 2 does not have any interesting invariants, right? So what does point 2 promise about its x and y coordinate? Well, nothing, right? So occasionally, so I ask this question on a quiz. I ask you, what are the point 2 invariants? You should say nothing. Sometimes a student will say, well, the value, the x and y coordinates are always double values, right? That's not really an invariant, right? That's just the way the class is implemented, right? So point 2 has no invariance of note, but that counter class that we talked about, that does have an invariant, right? So remember, the counter is this thing that represents a physical count. And that means that the value of the counter is never negative, right? So the counter invariant is that the value of the counter is always greater than or equal to 0, right? And for this particular counter, the value of the counter is always less than or equal to integer max value, right? And so if you look through the counter code, right, you can actually see that, in fact, this invariant is always true. Right? So let's look. So let's quickly look at the counter. Okay, there's our field called value. There's our first constructor, right? So it sets the value to 0. So is the value between 0 and integer max value? Yes, right? The invariant is true. There's our value method, right? Does it change this dot value? The answer is no, right? So assuming that the counter was constructed correctly, and everything else in the class is correct, right? We know that the value after this method is called is always between 0 and integer max value. So that's good. Now what about advance, right? Okay, so in advance, right, if we test if the value is not integer max value, right, and that's true, and then we can go ahead and increment it, everything's fine, right? So if that condition is true, I can safely add 1 to this dot value, and the value doesn't overflow. Right? If that condition is false, I can't add 1 to that value without it overflowing. Right? So we end up here, and that sets the value to 0. Right? And so if that is your advanced method, if that is your advanced method, our class invariants are still true. Everything's great. Now, if you implement the class incorrectly, so if you just simply increment value right away, right, you run into a problem. Right? If the value happens to be equal to integer max value, adding 1 to it causes it to wrap around back to a large negative value. Right? Right? If you try, oops, sorry. Right? So if you then try to test, right, is the value greater than integer max value, and then reset it back to 0, well, this test is never true, right? That never works, right? The value is an int. It can never be bigger than integer max value, right? So this incorrectly tries to set the value of the counter to 0, right? If that is your implementation of advance, right, your class invariance will no longer be true, right? If you call advance when the value of the counter is already integer max value. Right? So there's an example of when your invariant would become false. If your invariants become false, you know that there's something wrong with your code. Here's the toString method. Right? toString doesn't change the value of the counter. So assuming the constructor did its job properly, and assuming advance does its job properly, that's fine as well. Right? The value of the counter will be between 0 and integer max value. So just like testing the postconditions, you can test whether or not the class invariants are true. right? This is a little bit easier to do because the class invariants are the same for the entire class. So you can write one method that tests if the invariants are true. So I've got a private method called check invariant, right? It simply asserts that the value is always greater than or equal to 0. Right? Again, if that's not true, if that's not true, the assert statement will cause your code to stop, assuming you have assertions turned on. Right? It's a private method because we're only going to use the method inside the class. Right? No one using the class needs to explicitly check the invariants. Right? The class itself is responsible for checking its own invariants. So we can make this private. Right? And now after every public constructor or method, at the very end, simply call your check invariant method. Right? So there's another constructor that sets the value to that, to the specified value. Right? Notice that if you inspect the code, right, the code tests whether or not the incoming value is less than 0, and if it is, it throws an exception. Right? Otherwise, it sets this dot value to value. So the invariant is also true for this constructor. Right? This constructor never lets a counter be constructed with a negative value. Right? There's the copy constructor. Right? Assuming that your counter class is implemented correctly, right, the value of any counter will always be between 0 and integer max value. Right? So the invariant should be true here as well. Right? And there's value and there's advance. Right? And you can do the same thing for toString as well if you wanted to as well. Oh, I guess I did. Oh, here, right. Oh, yeah, right. So here, toString returns a value, so we have to check the invariant before the return statement. Right? Again, notice this is technically incorrect. Right? If that return statement does something to the value, then this checking of the invariant won't guarantee that this method is correct. Right? So again, Java is not one of these languages that does this sort of testing for you in a robust way. Right? But again, there are languages that will do this for you. Right? So the languages that test pre and post conditions will also test class invariants for you. All right, so that is preconditions, postconditions, and class invariants. Any questions? All right, moving right along. So I'm not 100% sure I have the correct set of lecture slides uploaded for this lecture. So I gave this lecture in CMPE 212 the other day, and this was the set of slides that I used. Hopefully these are the same. If they're not, I'll upload this set of slides and replace the ones that are there right now. This is, or should be, the slide set number 14. Okay, so UML class diagrams. So there's this thing called UML that you're going to encounter if you do more computing science courses. In particular, if you do the software engineering courses, you're going to run into these UML diagrams. So UML is a visual modeling language. So it's a language that's basically made up of pictures. Right? It's used in software engineering for visualizing the design of a software system. So that picture there is a UML diagram that illustrates the UML language. Right? So we're using UML to describe itself. You can see that at the top here, there's this thing called diagram. Right? So in UML, right, everything's a diagram. There's two main types of diagrams. Right? There's behavior diagrams and there are structure diagrams. Right? So behavior diagrams describe the behavior of your classes or objects. Right? The structure diagrams describe the structure or the structure of your classes or objects. Right? Now we're only interested in that thing here, right? The thing called the class diagram. Right? And obviously there's lots and lots of other diagrams here, right? Which you'll learn about in your other courses. We're interested in that one right there. So a UML class diagram simply describes the structure of a class, right? So what makes it the structure of a class? Well, the name of the class, the fields of the class, right? The methods of the class. Right? Later on, we're going to extend this idea. So when you have objects that are made up of other objects, you can use a UML diagram to describe the relationship between those objects. Okay, so every UML class diagram starts with the name of the class. Right? And then optionally, you can put in the fields and methods. Right? So that's the simplest UML class diagram that you can have. Right? It's just a box. So every class is just a box. The name of the class is supposed to be centered in the box and look like that. Right? So that's the only mandatory information you need for a UML class diagram. If for your particular purposes you want to describe what are the fields in the class, right, you can add those by appending another box or a compartment below your class, below the box containing your class name, and you put in your fields in that compartment. Right? Now, UML it's not designed specifically for any one language, right? So it has a generic notation for describing its fields and methods. Right? So the way you describe a method is you first put in the access modifier. So in this case, it's minus. Right? Then you put in the name of your fields, so X and Y. Then there's a colon, and then it's followed by the type of your field. Right? So, whoops, sorry. Oh, hang on. Double. Is it right there? No, it's not right there. Like that. Right, so access modifier, field name, colon, and then type. For your access modifiers, there are the 4 access modifiers, right? So plus is public, minus is private, right? The tilde is package private, and the hashtag is protected. Right? We'll look at protected later on in the course. Once you put your field, so if you've put your fields in, whether or not you put your fields in, it doesn't matter. If you want to, you can describe the methods as well. Right, so the methods are described in a similar way that the fields are described. There's an access modifier, then there's a method name. Right? Then there's the parameter list, and then there's the return type. Right? You can also include constructors as well. Right? So for point 2, if I fix the type again, so for point 2, we can add the constructors. So our constructors are both public, right? The name of the constructor is always the name of the class, right? Our constructor that takes in the X and Y coordinates has a parameter X, its type is double, right? It has a parameter Y, its type is double, right? So for the methods, it's similar, right? Access modifier, name of the method, parameter type, and then return type here. If your class implements an interface, which we haven't talked about yet, but if it implements an interface, you can also show that information on the class diagram as well. Right? So ArrayList implements this interface called list, right? And TreeSet implements this interface called sorted set. If you want to show this information on the class diagram, you draw your class, and then you draw a solid line coming off the class somewhere. It doesn't matter where, right? Left, right, top, bottom, doesn't matter where, right? Round circle, and then the name of the interface, right? And that simply says that ArrayList implements the list interface. We'll talk more about interfaces in probably next week, I think. Next week or after reading week. And so there's a very quick introduction to class diagrams, right? They're pretty easy to, they're pretty straightforward to draw. They'll become more useful to us when we talk about the relationship between classes, right? So when you start to make classes that are objects that are made up of other objects, these things become a little bit more important. Okay. So the next topic is related to this, is related to preconditions, postconditions, and class invariants, right? So preconditions, postconditions, class invariants, they're basically a mathematical description of your program, right? The idea is that if you can mathematically describe a program, in principle, you can actually verify whether or not the program is correct. Right? Now that turns out to be hard to do. Right? So the alternative is to, instead of formally proving your software is correct, is to test your software instead. Right? Okay, so testing code, at least for now, is a vital part of the development process. Right? So the goal of testing, when you test your program, you're not testing, is the program correct? Right? What you're doing is you're looking for bugs or errors in your code. Right? So testing, if done well, it can be an effective way to show that bugs are there are mistakes in your program. Right? But it doesn't matter how much you test, in most cases, right? It is not useful for actually proving your program is correct, right? So testing looks for bugs. It's not proving correctness, right? Edsger Dijkstra was, I don't remember if he's still alive or not, is a pretty famous mathematician and computer scientist. All right, so in the previous lab, so this was written for CMP 212. So in your assignments, so strike that, in your assignments, right, you might have been using a main method or multiple main methods to test your code, right? So I don't know how you actually did your assignments, right? But hopefully you did some testing of your code when you did your assignments, right? So for assignment 1, maybe you just wrote that test sorts program and then looked at the output and said, yeah, that matches what the prof said it should be, so my code is correct, right? So if you use a main method, basically you're creating a program that uses your code, right? That's all your main method is, right? When you do it this way, what ends up happening is you have to look at the output, right? Someone has to inspect the output of the program, right? To determine whether or not the code the tests that you wrote, whether they passed or failed. Right? So for assignment 1, you might have looked at the output of your test sorts and said, yeah, that matches what the professor said it ought to be, right? Or you might have said, hey, that's different than what the professor has. Maybe there's something wrong. Right? So someone's got to look at the output, right? If you have a gigantic program, right, and you try to test your program this way, right, you're going to have an enormous amount of output, which you then have to manually look at. So not only is that not fun to do, that's very unreliable, right? It's very easy to miss a failed test case. The other problem is if you do this is that all of your tests end up in one method or end up being called from one method somewhere, right? So for example, test sorts, all of our tests are basically in the main method of test sorts. Right? If you see that something failed, right? So imagine your selection sort method failed, right? You can't just run the test for the selection sort method again, right? You end up running all the tests again, or you have to comment out all the other tests manually, right? So that's no fun, right? I can't pick which test to run if I know which method is failing, right? I have to run them all. Right? So is there a better way to do this? And the answer is yes, there's lots of better ways to do this, right? And the answer is you want to find a test framework to write your tests, to help you write your tests. So in Java, JUnit is one of the very well-known testing frameworks. It's not the only one, there's lots of them. JUnit is certainly the one that most programmers will have heard of before. Right. So what is a framework? So a framework is just a semi-complete application. You can think of it as just being a library of software. Right? A framework gives you reusable common structure to share among applications, right? So in other words, JUnit gives you a bunch of methods and classes and other things that you can use to build a testing program, right? You can reuse all of the stuff from the JUnit framework to write tests for all sorts of different programs. Right, and so JUnit focuses on what are called unit tests. There are many, many, many other kinds of tests, right? And you'll learn about these other tests as you progress through computing science, especially if you take the software engineering courses. right? So what is a unit test? So a unit test just examines the behavior of a distinct unit of work. Distinct unit of work just means the smallest piece of code that you can call independently. Right? So what does that mean for Java? It means basically your units are methods. Right? So JUnit is essentially a framework for testing methods and constructors. Right? I guess we're basically out of time, so I'll show you what a JUnit test looks like at the start of the next lecture.